Now let's talk about what corresponding math, okay? I talked about the knowledge and then convolution can give you that, right? But more than that, okay, what corresponding math or change in the operations are, motivated by this knowledge? So I will talk about convolution we talked about before, but we'll also talk about channels, pooling, strides, and padding, okay? And we'll ask how much can be saved and what else can be saved. So let's talk about the concepts. Okay, so this is what we have learned so far. So first thing I want to talk about the additional concept. The first thing is the channel. Okay, so channel is the following. I said before that each image data is consists of a lot of pixels in the 2D grid. And each pixel could be one numerical value or multiple numerical value, right? So if it has multiple numerical value, for instance, RGB or CYMK, then we can call each like a channel, right? So in this case, there are the 3 color channels, right? But in other cases, you may parameterize your image data in different ways and you have different kind of channels, right? So this is what the channel means, right? So this is another strength of GPU in this kind of multi-channel introduction, because if you think about this multi-channel, right? So you can actually, previously if you have a single channel, right, you do this matrix multiplication or convolution in this way, right? But if you think about multiple channels, you can, imagine as if there is an additional dimension, which is like a depth of this paper or the screen, okay? Then you can overlay these different channels behind this first channel. It's like the additional dimension, right? So now you don't just have a matrix, you have a tensor, right? And then you can do the convolution or other kind of linear algebra in the tensor space, right? So, if you think about why some products are called TensorFlow, right? It's really very convenient. And the output could also have multiple channels, okay? So sometimes you want multiple readouts, and you could use multiple output. And how do you do multiple output channels? That means, like in this case, you have like, if you want 2 output channels, then it's like you are using, 2 sets of kernels, right, along this dimension. All right. So in the most popular neural network architectures, we actually increase the channel dimension as we go higher up, and then this will downsample to trade off the spatial resolution for greater channel depths. Okay. So so this is what channel means. Any questions so far? So the next concept, let's look at a bigger picture of a regular convolutional neural network, right? That we know about these convolution operators already, right? And then we are more or less familiar with the nonlinearity, right? And then there will be pooling stage involved, and then it will be fed into the next layer. So these are the additional concepts we're going to talk about, right? First, if you remember our 320 by 280 image, I said the output is going to be 319 by 280 because your kernel will start with the left boundary and it will stop when its right boundary hits the right boundary of the image, right? So it will be 1 less if the kernel is of size 2 in the horizontal dimension. If it's size n in the horizontal dimension, then your image will reduce n-1 pixels horizontally, right? So the question is the following. If we start with 240 by 240, and then we use 10 layers of a 5 by 5 convolution, in the end, what's the size of the output image? If you know what convolution is doing, any volunteers? You must know. Yes, Ryan? Don't be shy to try. 236 by 236? Okay. Uh-huh. Correct, but 10 layers.
The layer I'm not sure about.
10 layers, you know it. Your answer is for 1 layer. Correct. So after each layer, you will lose 4 pixels along either direction. Is that right? So it's going to be 200 by 200, right? Right? After each of the layers, you will lose 4 pixels along either direction. That 4 comes from 5 minus 1 and 5 minus 1. Okay? So, in other words, after even 10 layers, you will lose like 30% of the size, and you know, and also it doesn't consider any interesting information on the boundary. So apparently that's not desired. Okay. So for that reason, we introduce padding, right? So right. So if we have 0 padding without padding, this is what we have, right? So this is another way to illustrate what we calculated before, okay? So that's why, it keeps reducing, right? Right? So here you see 1, 2, 3, 4, 5, 6. The kernel size is 6. So after 1 layer, you should have, 5 less, right? So that's how the size is changing. But if you use padding, okay, you pad pixels outside of the boundary and give 0 values, meaning that's what we call 0 padding, then these black points are 0 padding, okay? So that's what you have. Then you see that in each layer we keep doing this 0 padding, and then the size does not change actually, okay? So that's what padding means. Third concept is stride. At the beginning, when I was introducing convolution, I said that if you overlay the kernel on the local patch of the input image, and then you move to the right 1 unit, and then another 1 unit, and so on, there I already assume that the stride is 1. So that's what the stride means, right? But you could have different possibilities, and apparently the stride also matters, right? When Ryan was saying that it's 4 pixels less each time we pass a convolution without padding, right? But that's also assuming that we are using a stride of 1, isn't it? Right? Okay. So you could use different strides, apparently, right? For instance, in this case, right? So in this case, I'm using, it's a 2-dimensional image. I use 3 for the height and 2 for the width, okay? So let's think about this. It's a 2 by 2, right? It's a 2 by 2. And then for the width, I'm using 2. So first it's here, and then the next is here, right? 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 So the first time is here, and then move to the right by 2 is here. And then I stop here, because if I move by 2 again, I will hit the boundary. And right now, I'm not using padding yet, okay? And vertically, let's try it again. Vertically, I'm using a stride of 3. So I start from here, and then I move down 1, 2, 3. I would start here, and then that's it. So in the end, I have a 2 by 2, okay? So apparently, you have to make the math a little bit more complicated when you are calculating the output size when there is no padding and the stride is not 1, because you have to consider this division and the remainders, okay? Okay, so now if we have a convolution with a stride, what is it like? Okay, so this is a convolution we have seen before, right? And you can see that this is the kernel, right? Overlaid on pixel 1, 2, and 3. And then I have a stride of 1, so now the kernel is on 2, 3, and 4. That's why you have these arrows, right? And then I move to the right again, and I have these arrows, right? If the stride is true instead, so when it's first here, right, then we have these output arrows. Then we move this kernel by by 2 instead of 1. Then next time we move it here, the center is here. Then this is the parameters. This is the operations you will observe. So this is a clear difference. It's making things even sparser, right? So let's try to summarize padding and stride a little bit. So now you understand the concept, right? And what we do with it. So padding can increase the height and the width of the output, right? This is often used to give the output the same height and width as the input, right? That's something is clear. The stride apparently can reduce the resolution of the output, right? For instance, if the stride is an m bigger than 1, then apparently you're reducing the height and the width by a factor of 1 over n, right? So without padding, you are just losing some number of pixels, but here you're scaling the height and the width. So it's like reducing the resolution, right? Much more drastically. So padding and the stride can be used to adjust the dimensionality of the data effectively. So that's something that can be counted on. The last concept is pooling. Okay, so pooling. So let's look at this case, right? So what we did here is, previously we have a kernel, let's say 2 by 2, and let's say A, B, C, D, right? 4 elements. What we did was multiply A by 0, multiply, B by 1, and so on and so forth, right? So that's kind of, you can also think of it as like a local summary, right? So that's what convolution does. What pooling does is also like a local summary. Okay, but it's not using convolution, like in this case. It's a 2 by 2, which defines the locality, and the type of pooling is max pooling. What it does is find the maximum in this 2 by 2. In this case, it's 4. Okay? And if you use a stride of 1 and then move on next, then you have it here, then the biggest is 5. That's 5 here. And then the biggest here is 7 here, and biggest here is 8. That's 8 here. Okay? So just like a convolution, pooling slides a fixed size window, right, over all regions according to its stride, right? If it's maximum, that's what we have seen before. You can also have average pooling, right, which gives you the average value and so on. So, but just like convolution, that's what's similar, but unlike convolution, pooling does not have any parameters, right? I don't have any element here. I know that it's already defined. I'm using the maximum or the average. There's no parameters to learn. Okay? Okay. So now let's try to see what these operators can bring to us, right? So what does this bring to us? Don't forget about how we learned from our vision system. This pooling is very similar to convolution in the sense that it's invariant to translations, right? Thanks to the same kind of fixed size window, the same kind of window, and sliding over all regions. That is maintained, but it does not have any parameters. So in other words, it can help you, reach some multi-scale. Right? For instance, you can gradually aggregate information from the first, and then to the last layer, and then you gradually reduce the scale of the hidden dimension. So that's like giving you a coarser and a coarser map. And you can actually scale up as well. That's a UNet, right? So let's look at max pooling and its invariance to translation, right? Something I mentioned here, right? But now let's try to visualize it again, right? So let's look at this case, right? So if we look at this size, again, this max pooling is fixed. What should I call it? I don't want to call it a window or kernel, right? But anyway, the size, this max pooling is 1/3 here, apparently, right? You can tell right away, right? It's 1/3. So the biggest value here is 1, apparently, and the biggest value here is 1, and so on, right? Let's say the input is shifted to the right by 1 unit. You see that 0.1 is shifted here, 1 is shifted here, 0.2 is shifted here. There's a new value here, okay? Now, let's look at what this max pooling does to the translated original image. Let's look at the output. What did you see? What did you conclude about the output? Right? The output is also shifted, right? 111 versus this 111, right? And you can do pooling with downsampling, depending on your pooling window size, right? So you can downsample, right? And in this case, how do you downsample? You actually do a pooling with a stride, right? So what's the stride here? Here is a max pooling, apparently, and it's a 1/3 max pooling. What's the stride of this 1/3 max pooling? 2, right? 1, 2, right? Okay, and this pooling, now we have learned a lot of things, right? But they can be all put together, make things even more complicated. We talked about channel, we talked about pooling, we talked about stride, we talked about the kernel size, right? So now let's try to mix them even more, right? You could do pooling cross-channel. Okay, you could do pooling across channel, right? And let's look at this example. Okay, so this is MNIST. We are just detecting 10 digits, right? It's 0 to 9. This is a 5, right? So these are different, handwritten 5s, right? And then in this case, let's say we have multiple detectors, multiple channels, right? And then in this case, there's a large response in detector unit 1 here, right? And then in this case, you have the large response in detector 3 here, right? So these are different detectors, are like different channels, right? Then you can actually pool them together, for instance, the max pooling across the channels, and you get the same large response in the pooling unit, okay? So now let's summarize pooling again. So let's see what pooling is doing is that it takes the input elements in the pooling window and it does something very similar to convolution, right? For instance, it's doing the maximum pooling or doing the average, right? But it does not have any parameters, right? So one intuitive way to see what they are doing is, in the case of the maximum pooling, it's bringing out the lighter foreground, right? If you think about the grayscale image, right? The lighter pixels are over higher values. So if you are doing the max pooling, you're basically bringing out the lighter foreground, right? Because the foreground is usually lighter, right? and larger pixel values. If you do the average pooling, it's like you are smoothing the whole image. And then what you may lose is the sharp edges, right? Right? So one of the major functions of a pooling layer is to alleviate the excessive sensitivity of the convolution layer to the location, okay? And we can specify the padding and the stride and combine and use the channels even together, right? And the max pooling combined with a stride larger than 1 can reduce the resolution. And the pooling layer's number of output channels is the same as the number of input channels. Again, you could have multiple channels as well, okay? Any questions so far? We talked about the few important operators in the convolutional neural networks, right? So again, this is just another example, like a classification architecture, right? Again, you start with the input image, right? And you do convolution, and then do a ReLU, and then this is a new size, right? And then you do a pooling with a stride 4. I would strongly recommend you to pay attention to these numbers to make sure that you understand them, right? If you understood the concepts taught so far, you should be able to, prove or, calculate by yourself and prove that it's the same as what's shown here, okay? And this is one example, okay? Let's say there's an input image. Again, I'm writing this number 2, right? Then the convolutional kernel is 5 by 5, right? So it slides with a padding. Here there's no padding. So I'm getting 4 less in each dimension, and I'm using N1 channels, okay? Then I do a max pooling 2 by 2. Then what it's doing is it's reducing the resolution by a factor of 1/2 in each dimension. So then I reduce to 12 by 12 times N1, and I do a max pooling, and I do convolution again, and then I do the max pooling, and then you see this 4 less, and then scale by half again, right? But this N1 has changed to N2. Okay, this is another thing you have to pay attention to. In the end, I do a readout through the fully connected layers. Okay, there's a nonlinear activation here. Okay. Again, this was introduced. So what has happened since LeNet, right? So there's a lot of the applications apparently, right? And it's used for image recognition, like. For each pixel, you can classify what it belongs to, right? And then if you think about what I said, how deep learning has picked up again thanks to the ImageNet. This is AlexNet, right? This is AlexNet, right? So this is the same model as LeCun 98 or LeNet, but it is a bigger model. It has more data. And also it has already GPU implemented, and then better regularization, it used dropped out. So if you wonder why LeNet was already born in 98, but why it took until 2012 or 11 ImageNet for CNN to be picked up, these are the reasons, right? One of the key reasons is there was no ImageNet back then, and GPU wasn't that powerful, okay? But this dropout is a great idea. We talked about regularization, right, before, in the case of the shallow models, right? In the deep models, in this case, dropout is a very effective way to regularize model complexity, okay? Okay, so after LeNet, what else can be done? There are a lot of things that can be done, but I'm not able to introduce them into a lot of details, right? You could have local connection, but without sharing, right? Compared to the convolution, right? It's somewhere between the convolution and fully connected, right? So this AB is shared in convolution, but it's no longer shared in this kind of cases. It's still local, but not parameter sharing, okay? What else can you do? You can do tiled convolution. You can cycle between the groups of shared parameters, right? So you have A, B, C, D, then A, B, C, D again, right? right? So this is a tiled convolution. And there's a partial connectivity between channels, right? So the connectivity can be restricted, right? And there are a lot of things that can be done. So, but if you look at the ImageNet, the winners after AlexNet, right? So then you have seen the VGG, GoogLeNet, right? It's you see this LE here, right? That's standing ovation to LeNet, right? And then ResNet you're familiar with now, and then SENet and so on, right? Some of you will talk about VGGs or UNet. So these are the summaries, fully convolutional networks, networks using blocks like VGG, and then inceptions used in GoogLeNet, and ResNet using the residue blocks. So some of them will be mentioned in your journal clubs as well. Okay. And convolution can be done not only on images, but also on graphs. So we probably want to talk more about it in a dedicated graph neural works. But this is an illustration of how graph convolution is done. It's very similar, but just different structure. It's no longer a grid structure, but a graph structure. So you're looking at a local region, which is now defined by the connectivity. So this is now a neighborhood, not a grid patch anymore. So let's see. What we have learned so far, right? So we have seen how knowledge drives math. We have learned that seemingly so simple ideas like convolution, channels, pooling, strides, padding actually have so many great properties. And if you have to think about it, what we are learning is assuming that we have these properties, these operators, and we see that great they have these properties. But how were they developed? Again, people actually started with the desired properties, learned from the vision systems, and then they designed mathematical operators to accomplish that, right? And we also learned how much can be saved compared to the dense net, and what else can be done, right? So some summaries of the recent works, right? So in the end, I'd like to talk about two case studies very quickly. I'd like to use the same protein structure prediction as an example. We have learned how it's done in the classical world, right? The three scenarios and then different formulations, right? So now, if you think from the data perspective, right? Of course, we can do it now because there are more data and more computing power and more sophisticated AI models. But what can we do now, right? Do you see any images in the problem of protein structure prediction? Well, I'm going to talk about two simpler versions of protein structure prediction. The input is the 1D sequence, but the output is not necessarily the 3D structure or the coordinates of all atoms. The first simple version, I call it a 1D problem. In other words, we are only predicting which fold the structure belongs to. Okay? So it's like a 1D summary of the 3D structure. So is this a regression problem or a classification problem? Classification, because the labels are discrete, right? We have thousands of labels. So in this case, what they do is DeepSF, they start with a sequence, G, I, V, and so on. Then you featureize every position, okay? What they have is like a 45 dimension. The first 20 is a one hot encoding of amino acids. The next 20 is a position-specific scoring matrix or profiles, both of which I've learned before. Then the next three are categorical predictions of the secondary structure, alpha, beta, or loop, right? Categorical. And lastly, it's a sequence predicted solvent accessibility, buried or surface. So in other words, they rearrange this into a L by 45 dimensional matrix. Then they run through the convolution layers. They actually have 10 channels, right? Then L by 2, right? And 10 filters, and then 2 filter sizes. And then they have these 10 layers, right? They have 10 layers, and then 10 layers, and then 10 filters, right? And then 2 different filter size, right? And then they do a pooling afterwards, right? Again, and then flatten them, and then in the end you have the dense layer to have the readout. So the readout is 1195. This number 1195 is the number of folds. So each output here is essentially, like a probability. Okay, so I assume that they have a softmax at the end, right? Because the sequence can only belong to one fold, right? In the simpler setting. The question here is, where are the images? Why are they using CNN? Where is the image here? What image do you see in this case? I cannot see you, Rujie, but I will just ask you. Where is the image in this case? The input, L by 45, right? So they treat it as image and use CNN. How much do you agree with that treatment? Is this image like the natural image? Is there anything special about it?
So I think it's like the width of this image.
Mm-hmm.
So you cannot just crop something out. Just treat it.
So in other words, the structure in the horizontal direction is not as the natural images. Is that right? Right? It's very sophisticated. It's not even tabular data either. Because you know that these first 20 are one-hot encoding. So there's some, dependency, between these 20. And then this 3-dimension is also categorical, right? It's one-hot again, and SA is one-hot again as well, right? So it's actually a very special structure that I think it will take the convolutional neural network a lot of data to learn this, right? But nevertheless, that's what people, still do, but I think gradually they are being revolutionized. Another example I want to show you is a 2D version of protein structure prediction. What I mean by 2D prediction is, let's look at the output. I said that there are different ways to represent a protein structure. One way is to look at the contact map. If you have L amino acids in the sequence, then you can look